All right, welcome everyone. Today we're going to get started on the big, kind of, if you will, shortcut, the big discussion for actually computing these integrals, finding the area under a curve, right between the curve and the x-axis. So let's get to the .cam and start to learn through this. All right, so here we are, looking at the fundamental theorem of calculus. This idea, this fundamental, like this basic, not basic, sorry, but this kind of major idea, theorem, that's really going to relate the two main discussions with calculus. Okay, it's going to kind of unify our derivative work now with, now with our integration work. Okay, and so let's recall, let's think back for our notation. Okay, that when we have that long stretch S of yield, this elongated operation, this is the integral symbol. We have our limits of integration, a to b, the lower limit, upper limit, right? Again, talking about the relative location as well. Also talking about the interval over which we'll be integrating. We have our function f of x, the integrating factor, I call it dx. And so when we see this integral, right, the integral of that function f of x, our integrating factor dx, the integral of x, from a to b, right? That's kind of how I would read it. And we would identify this to mean this is the area under the area between that function f of x over the interval from a to b. And again, we have mentioned that with this area concept, it can also be negative if that function happens to go below the x-axis, just out of ease in consideration and thinking, in viewing. We start off with just kind of that typical graph in our first quadrant where everything's positive, but of course, it's perfectly fine if that function is negative, all right? So if we have this function, my go-to curve here, there's my function f of x. We're going to integrate over this interval from a to b, and we're trying to identify that area, okay? So the integral is equal to this precise area. And what we had been working on previously was kind of estimating, approximating that area with rectangles, right? There'll be other figures and whatnot we can use, okay? With computer science, they talk about programming, different techniques, tools for doing these integrations and so on, solving these problems by using little figures and calculations, picking which representative value x we're going to use to plug into our function, so on, all that work we can program into the computer to start to do that kind of calculation with those rectangles. But now our fundamental theorem is going to give us our more precise way, our shortcut way of finding those areas without having to go through that limit, go throughout the rectangle process of approximating, okay? So for now, let's define, let's create a function using the integral, all right, using an integral. All right, so let's say, in this case, we're going to create this new function, g of x. That's going to be equal to this integral from A to some value. So there's my dependence, right? Depending on how long, how wide the interval we want to make from A to some value x, okay? For some function f of t dt. This is what we call like a dummy variable, just kind of the stand-in variable, this parameter, because depending on what value we choose for x is going to determine how much area, how far along on the curve we want to produce. So we can identify, now this is my variable t, be careful there. We have our function, again, similar to what we had done before. Actually, you can go onward, sorry. But we have our function f of t. And in this case, we're going to start at some value a. But now, this quantity x that we're depending on is going to determine how wide that interval is, right? And so in this case, that area, that integral, that's going to be equal to my g of x. And depending, let me slide this up, sorry. Depending how big, how small we choose for x away from a, it can be really big value, getting more area. It can be really small amount of area. But that quantity, depending on how big we make that interval, how far we're going to integrate to, that's what that g of x is, right? And so we might be able to kind of see that if I let x equal a, right, I don't let it get any far at all, there's not going to be any area. It's just that little sliver line. There's no area there, so that would be 0. And then we can start to take, okay, a little bit further, that area starts to grow, okay? All right, and we'll come back to some of these properties of these integrals once we actually start to compute, okay? But now, if that's my g of x then, okay, with that, let's consider g of x and g of x plus h, right, where h is some value, we're going to be a little bit bigger, right? Some x value, then some value just a little bit bigger. So in that case, hoping to not get too cluttered here, if we have our same function, f of t, and again, remember, here, g of x was equal to that integral, that amount of area from a to x underneath that function f of t, okay? So when I look at this amount of area, there's my g of x, right? That amount of area was our g of x, like we had before. All right. So then now, if I look at here, x plus 8, so it's going to be that x, then add a little bit more to it, right? Like 1, it's going to be 1.1, 1.2, something like that. Now, this entire span from a to x plus h, there's that total area is a g of x plus h. Okay. So like think about it, we have this little bit of overlapping. And so now what we're going to really focus on though, let's think about that area. Okay. What about this area? This edge was my x. This edge was x plus h. We have our curve up top, that f of t. Okay. What about this area? Well, looking at our picture, from a to x plus h, that area is going to be this g of x plus h, that integral. This area from a to x is that function, that integral g of x. So if I want to get this little space, well, I could take that total area, take away, slice off, cut off this region, and I'd be left with just that portion. So that area, okay, that area in little strip, right, a little strip of area, that's going to be equal to that g of x plus h, the area, the integral from a to x plus h, minus g of x, that area from a to x, right? So that's going to leave me a little strip, the little space of area in between. And if we try to approximate, okay, this height component, if this is my function, f of t, the height then, well, if I pick this particular x, that's going to be f of x, right? If I use that side. If I do the other side, x plus h, we could do that as well. Very similar. In between, this width, how far apart are they? How wide is that little strip, the little rectangle that we're going to overlay to get from x to x plus h? That width is going to be h. So in this case, that area in the strip as a rectangle, we can approximate is that f of x times h, the height times the width. And that's going to be, approximately. It's not going to be perfect. There's a little bit of arc there, but it's approximately g of x plus h minus g of x. And hopefully this is starting to look familiar, even back here, g of x plus h minus g of x, that looks like our derivative, right? So if I divide both sides by h, this f of x approximately g of x plus h minus g of x all over h. And at this stage, right, this looks like a derivative, right? So if we take this limit as h goes to 0 on both sides, right, doing that same operation, that same action, taking that limit as h goes to 0, that's exactly what we had used for our limit definition of the derivative. So in the end, looking at it, well, that f of x didn't have any dependence. How we did the x plus h, that right-hand side of the rectangle, then h goes to 0, that would become f of x plus 0, or just f of x, right? So in this case, we get f of x, I'm going to go precise, equals now that limit as h goes to 0, g of x plus h minus g of x over h, that's g prime of x. So that function is equal to that derivative of g of x. So now bring it all the way back to the beginning. Well, remember that we had said that g of x was that integral from a to x of that function f of t dt. So now, with what work we had just completed, when I take the derivative g prime of x, we're getting f of x. And there's our fundamental theorem, the first part. The major idea here with this first part of the fundamental theorem of calculus, part one, right? The key concept that I want to kind of really emphasize is that notice the derivative of that integral, right? So there's this relationship between these two major concepts, the derivative and the integral. The derivative of the integral is that function we were finding the area below. Right? Or not a precise mathematical statement here, but notice that that derivative basically, I'll say kind of, undoes or cancels or is the inverse, or not necessarily, it's not great mathematically, but this kind of thinking, that integral. Right? We have this idea that if I have my g of x equal to that integral, when we take the derivative with respect to x on both sides, right? We're getting our g prime of x. On this side though, right, basically what happens when I take the derivative of that integral, the derivative and that integral go away, I just need to drop my variable x into my function, right? Because our function depends on x, so that's what belongs. A minor component with this fundamental theorem, the lower bound always has to be a constant, whatever constant you want, 0, -1, +1, 105, whatever you like. A constant down below, variable for our upper limit. Okay, and then once we do so, when I take the derivative, that term drops out. And that's the real kind of start as we begin this. There's another major component I'll talk about in a moment, that derivative is going to cancel out that integral. Okay, so a quick example here. If we were given that, let's go capital G of x this time, is equal to this integral from 3 to x of this function, say t cubed minus 4t plus 5 dt, and we want to find the derivative g prime of x, right? So kind of going through, taking that derivative with respect to x on both sides, taking that integral, now finding its derivative. G prime of x is going to be equal to, and now over here, that derivative, that integral go away. And now wherever I see the variable, that x, it needs to replace. So we get x cubed minus 4x, that constant still present. And there we are. Okay. And then later, we can look at some examples in the text with some of the previous written notes, or even with our lecture slides from the text, that if we have a function here, right, x squared cosine of x, we do that same work. But again, if this is a function of a function, we need to do the chain rule. So we do this work of substituting whatever that is into a part variable, and then we multiply by the derivative of that upper limit, that variable limit, as that chain rule. In this case, really x is just 1, right? So multiplying by 1 doesn't change anything. Okay? So we can kind of see that work with that fundamental theorem of calculus. The first part relating the integral and that derivative. Okay? All right. Let me stop here, and I'll make the second part of a fundamental theorem its own lecture as well.